Good morning, class. We are looking at trigonometric identities. So we looked at trigonometric equations. We are going to look at trigonometric equations involving identities. We're going to use algebra to simplify trigonometric expressions and establish identities. Again, reminding everybody about the graph of a sine and cosine function. We basically have the period of 2 pi for sine and cosine, basic sine function and cosine function. We cut it into 4 pieces, 4 arcs. We established that sine x is cosine of x minus pi over 2. And in the case of y equals a sine omega x or a cosine omega x t, which is originally 2 pi, is now 2 pi over omega. None of the trigonometric functions are one-to-one. They don't have inverse unless we do the restriction, and the restriction will make it happen. And now they have inverses. So for example, for sine and tangent, we restrict it from minus pi over 2 to pi over 2. For cosine, 0 to pi. Now, the same fundamental identities that we've seen, it works out here. First of all, two functions are considered identical if f of x equals g of x. For every value of x for which both functions are defined, such an equation is referred to as an identity when it comes to trigonometry. There are fundamental identities that we have discussed, starting with the unit circle, x squared plus y squared equals 1, and x is represented by cosine, y is represented with sine. We looked at the periodic functions. Every trigonometric function is a periodic function with a period of 2 pi, except tangent and cotangent. Then all of them are odd functions with the exception of cosine, which secant follows as well. We have Pythagorean identities. Sine squared plus cosine squared is 1. Tan squared plus 1 is secant squared. 1 plus cotangent squared is cosecant squared. We have quotient identities. Tan is sine over cosine. Cotangent is cosine over sine. And reciprocal identities say cosecant is 1 over sine. Secant is 1 over cosine. Cotangent is 1 over tangent. So we have those, and now we are going to look at more. For example, we want to simplify the expression of tan theta over secant theta. So we are going to rewrite it in terms of sine and cosine. Most of the time, that's the way it works. We know tangent is sine over cosine, and secant is 1 over cosine. So you're dealing with a complex fraction. The denominators are identical. You can drop them. So you get sine theta over 1 or simply sine theta. We want to show that sine theta over 1 plus cosine theta equals 1 minus cosine theta over sine theta. And they have given us a hint. Multiply one side, in this case, the left-hand side, by 1 minus cosine theta and divide by it. So the left-hand side, we are going to multiply and divide by 1 minus cosine theta. So what happens as far as the denominator is concerned, you get 1 minus cosine squared . 1 minus cosine squared is the same as sine squared. So this sine goes away, and this becomes sine theta. So this one and this one. So the denominator changes to sine theta. And that is the proof that they two are identical. All right. What about this one? We start from one side. And since we did the previous one, we notice we can do the same thing here. If we start with the left-hand side, we can multiply by 1 plus sine theta and divide by. Sometimes you can do the cross product, that's okay too. But if you want to go from one side to the other, establishment works out this way. So obviously the denominator is 1 minus sine squared. And we know 1 minus sine squared is cosine squared. This cosine goes away, and this cosine squared will change to cosine theta. So we are looking at this one going away, this one changing to cosine theta, and that is the right-hand side. That's the proof. So we are establishing identities. We want to simplify. And in this case, we take a common denominator, LCD, which means the common denominator is 1 minus sine u times 1 plus sine u. And the numerator would be 1 times 1 plus sine u plus 1 times 1 minus sine u. In other words, we raise each fraction by a factor of 1 plus sine u. So this gives us 1 plus sine u plus 1 minus sine u. And the denominator is 1 minus sine squared. These two cancel each other. The numerator changes to 2, and the denominator changes to cosine squared. As you know, 1 over cosine is secant. Therefore, this is secant squared. 2 over cosine squared is the same as 2 secant squared, because secant is 1 over cosine. We want to simplify this, and the technique is factoring. I hope you recognize the top is a squared minus b squared, because 1 is also 1 squared. So it becomes a plus b, that means 1 plus cosine, and a minus b, that means 1 minus cosine. As for the denominator, we have a common factor of sine v. We can take it out. When we do this, one plus cosine v from the top and the bottom cancel each other. And this is one way to write it as a final, but we can rewrite this into two fractions. 1 over sine minus cosine over sine. We know 1 over sine is cosecant. Cosine over sine is cotangent. And we are done. We are simplifying using LCD, the least common denominator, which is sine u times cosine u. So the first fraction will be raised by a factor of cosine u, and the second one by a factor of sine u. This is sine. So the denominator is sine u times cosine u. This becomes 1 plus sine u times cosine u, which is cosine u plus sine u cosine u. This one is cotangent u times sine u minus cosine u sine u. And again, the denominator is simply sine u cosine u. Sine u cosine u and cosine u sine u are the same. Since this has a negative sign, they cancel each other. So the numerator is left with cosine u plus cotangent u sine u. We're going to replace the cotangent with cosine over sine. So this part is cosine u over sine u times sine u, which simply becomes cosine u. So you have cosine u plus cosine u, or 2 cosine u in the numerator. You can drop the cosine u, and since 1 over sine u is secant u, this is 2 secant u. That's the simplified version. We do it by factoring. The numerator is sine v plus 1 times sine v minus 1. And the denominator has a common factor of tan v, gives us sine v minus 1. So we do the factoring. The common factor of sine v minus 1 from the top and the bottom cancel each other. We make up 2 fractions. And in the first fraction, we replace the tangent with sine over cosine. The reason we do that because this one becomes cosine v. It's a complex fraction. The sine and sine cancel each other and cosine comes up. And 1 over tangent is cotangent. So here's the final answer. Let me quickly fix this for you. So this is now fixed. And we are done with the page. We want to establish the identity. Normally, we start with the more complicated side, and sometimes it's hard to see which one, but this is clearly the left-hand side. So the left-hand side, LHS, the left-hand side, I'm going to change the cotangent to cosine over sine and the tangent to sine over cosine. So the left-hand side, I start with the left-hand side. Let me just spell it out. Left hand side. So from now on, LHS. And if I have RHS, the right-hand side. And so on the right side, I can take a common denominator of sine theta, cosine theta. So inside the parentheses, sine theta, cosine theta. So this one gets multiplied by this one, becomes cosine squared. This one gets multiplied by this one is sine squared. I'm assuming we can easily add up the two fractions. We know cosine squared and sine squared, they add up to 1. And we can drop sine theta. Remember, this is like sine theta over 1. Sine theta from the top, sine theta from the bottom. So you get 1 over cosine theta, which is secant theta. 1 over cosine theta, which is secant theta. We want to establish this identity, and we can start with the left side, which involves things other than sine and cosine, and change them into functions of sine and cosine. So the left-hand side, cosecant is 1 over sine, cotangent is cosine over sine. So that's the change we're going to make to the left-hand side. They have a common denominator of sine theta, so it's 1 minus cosine theta over sine theta. And if we want to establish the right side, and we notice the denominator is 1 plus cosine theta, and the conjugate of 1 minus cosine theta is 1 plus cosine theta. Let's multiply the top and the bottom by 1 plus cosine theta. Sometimes you have to look at what you're looking for to get there. When we do that, the denominator, we are going to keep it as a product and we're not going to touch it. But the numerators, when we multiply them, we get 1 minus cosine squared. So the denominator, we keep it. Now, 1 minus cosine squared is the same as sine squared. And that, we can drop this one and change this to sine theta, which is the right-hand side, and that's a proof. So in the process, you want to look at the other side and see what you want to establish, where you're heading. We want to establish the identity sine squared theta minus tan theta over cosine squared theta minus cotangent theta is tan squared theta. Clearly, the left-hand side is the more complicated side. So we look at each term and we notice we have tangent and cotangent. Let's change those. So this we are going to change it to sine over cosine. This we are going to change it to cosine over sine. We are dealing with a complex fraction. We find the common LCD for all of those fractions. And you notice this has the denominator sine, this has the denominator cosine. So we're going to multiply everything by sine theta times cosine theta. So we're going to multiply by this fraction, which is equal to 1. That means everything gets multiplied by sine theta, cosine theta. So what happens is that if I multiply this one by the first piece, I simply get sine cubed theta cosine theta. But when I multiply these two, cosine goes away and I get minus sine squared. When we multiply these two, we get sine theta cosine cubed minus, when we multiply these two, sine goes away, minus cosine squared theta. I hope everybody is comfortable with multiplication, simplifying complex fractions, understanding LCD. So again, when you multiply by this, you get this one. You multiply by this, you get this one. You multiply by this, you get this one. You multiply these two, you get this one. All we have to do, factor what we can from the top, from the bottom. We notice in the numerator, sine squared is in common. When we take it out, we are left with sine theta cosine theta minus 1. And in the denominator, cosine squared is in common. So the top, this is in common. The bottom, this is in common. We factor it as follows. Sine squared theta times sine theta cosine theta minus 1 over cosine squared times sine theta cosine theta minus 1. These two we drop them. And we are left with sine squared over cosine squared. We know sine over cosine is tangent. So this is tan squared theta. All right, we want to establish the identity cotangent squared is cosecant theta minus sine theta over sine theta. And clearly the right-hand side is more complicated. So we start with the right-hand side and we change the cosecant to 1 over sine. Change the cosecant theta to 1 over sine theta. It's a complex fraction. Let's multiply the top and the bottom by sine theta. So what happens is that when you multiply these two, you simply get 1. The others are simply sine squared. So you get 1, the rest of them become sine squared. So 1 minus sine squared over sine squared. The top is obviously cosine squared. Cosine over sine is cotangent. So the answer is cotangent squared. And that is the left-hand side, and it's the proof. We want to prove that 1 minus cosecant theta sine cube theta is cosine squared theta. So left-hand side seems to be more complicated. We start with that, and we change the cosecant to 1 over sine. So we get 1 minus sine cubed over sine theta. Sine cubed over sine theta is sine squared. 1 minus that is cosine squared. One establish the identity 1 plus tan u over 1 plus cotangent u is tan u. So the left-hand side seems to be more complicated. We are going to start with the left-hand side. And we're going to change the cotangent to 1 over tangent. Because ultimately we are interested in tangents. So it's a complex fraction. Let's multiply everything by tan u over tan u. So clearly the numerator, you just keep it as a product, tangent times 1 plus tangent, or 1 plus tangent times tan, doesn't matter. I hope you see that when you multiply the bottom, you get tan u times 1, which is tan u. And tan u times 1 over tan u becomes 1. So the product of these two is 1. So 1 plus tan u drops from the top and the bottom, and we end up with the right-hand side. Tan u, we established this identity. We want to establish this identity, and clearly the left-hand side having two fractions is more complicated. So we are going to start with the left-hand side. We're going to start with the left-hand side, and we're going to take a common denominator. Common denominator is the product of these two, and you multiply these two. That becomes a common denominator, which is secant squared x minus tan squared x. Then 1 times secant x minus tan x plus 1 times secant x plus tan x goes to the numerator. This is your left-hand side, assuming we have no problem with fractions, adding them up, finding LCD. So a quick recap. What is the LCD? The product of these two. What is the product of these two? Secant squared minus tan squared. 1 times secant x minus tan x plus 1 times secant x plus tan x. That comes to the numerator. And since everything has a plus sign, let's simplify the numerator first. So the numerator is secant x minus tan x plus secant x plus tan x. These two cancel each other. These two add up to 2 secant x. Now, as far as the denominator is concerned, I'm going to remind you of one of the Pythagorean identities, which says tan squared plus 1 is secant squared. And therefore, if I move the tan squared to the right, I get secant squared minus tan squared equals 1. So if the denominator is 1, the answer is 2 secant x, which is the right-hand side. So we just proved it. All right. We want to prove this one, and clearly the right-hand side. So we're going to prove sine x equals minus cosine x times tan minus x. And the right-hand side is more complicated. So we're going to start with the right-hand side, and tan of negative x is negative tan of x. So negative times negative makes it positive. So we simply have cosine x times tan x. So I want to make sure we understand what's going on. The product of these two, because tan of negative x is the same as negative tan x, negative times negative makes it positive, cosine x tan x, and we know tan x to be sine over cosine. So this cosine cancels out this cosine. The answer is sine x, which is the left-hand side, we just proved it. We want to prove that sine x over cosine x plus 1 plus cosine x minus 1 over sine x, they add up to 0. So clearly we start with the left-hand side, and we're going to take a common denominator, which is the product of the two denominators, cosine x plus 1 times sine x in any order. So the product of these two is the denominator. We are taking a common denominator, so sine x times sine x plus cosine x minus 1 times cosine x plus 1, which makes it cosine squared minus 1. So I'm going to quickly show you. So what this is clear. Sine x times sine x. What this one is cosine x minus 1 times cosine x plus 1, which makes it cosine squared minus 1. As you know, is to add up to 1. 1 minus 1 is 0. The numerator is 0, and the denominator is some number. 0 over a number other than 0 is 0. We want to prove the natural log of secant theta plus tan theta plus the natural log, ln is the natural log of secant theta minus tan theta is 0. So the left-hand side, ln, let me remind you, if I have ln x plus ln y, I can say ln xy. This is one of the properties of logs. Hopefully everybody remembers. So I can put them into a single log, ln of secant theta plus tan theta times secant theta minus tan theta. And I used x here, so class, you can imagine it's x. It makes no difference. It's a dummy variable. And either one is fine. So when we multiply the two, we get secant squared minus tan squared. And again, I'm going to remind you that tan squared plus 1 is secant squared. And that means if I move this to the other side, secant squared minus tan squared is 1. The answer is ln 1. And we should know ln 1 is 0. The answer is ln 1. And ln 1 is equal to 0. So we prove this using logarithmic properties, and I hope everybody remembers them. For example, log 1 base a is 0, log a base a is 1, log a to the power of x base a is x, a to the power of log x base a is x. These are logarithmic rules. Log x base a plus log y base a equals log x y base a. Log x base a minus log y base a is log x over y base a. Log x to the power of n base a is n log x base a. So I'm reminding you of important properties. A log of 1 is always 0 because a to the power of 0 is 1. Log of a is a when the base and the argument are the same because a to the power of 1 is a. And these two establish the fact that there is a relationship between exponential functions and logarithmic functions. They are inverse functions. This is called the product rule. This is called the quotient rule. And this is called the power. I'm reminding you of things we have seen. So I hope everybody is comfortable with the logs. Therefore, what I did here, in essence, I used the product rule. And remember, this is a general case. When the base is 10, we call it common log. When the base is e, we call it natural log. So I just wanted to refresh everyone's memory. I need this space. I'm going to clean up this mess and we're going to continue with the next question. All right, we want to prove that sine alpha plus cosine beta quantity squared plus cosine beta plus sine alpha times cosine beta minus sine alpha results in 2 cosine beta times sine alpha plus cosine beta. And clearly, we are going to start with the left-hand side. When we square this, we get sine squared plus 2 sine cosine plus cosine squared. Of course, sine squared alpha plus 2 sine alpha cosine beta plus cosine squared beta. When we multiply these two, it's cosine squared beta minus sine squared alpha. So the left side, simply put, do the multiplication. Sine squared will cancel out negative sine squared. So we have this, and we will combine this into 2 cosine squared beta. If we take the common factor of 2 cosine beta, we prove it's equal to the right side. We want to simplify cotangent over cosecant. There is a hint, even without the hint. Normally, one easy way is to write everything as functions of sine and cosine. So cotangent becomes cosine over sine. Cosecant becomes 1 over sine. You can do the extremes over the means, or just drop the sine x, and you get cosine x over 1, which is cosine x. By the way, again, just to remind you, If we have A over B over C over D, can multiply these two and put it at top, right? You can multiply these two and put it at the bottom. So just to refresh your memory about complex fractions. We start with one side. In this case, again, we start with the right-hand side and we multiply and divide by 1 minus sine theta. That's the hint, even if they didn't give us that hint, because the right side involves 1 minus sine theta, it makes sense. So let's do that. So what happens, you write the numerator as a product and the denominator becomes 1 minus sine squared. We know 1 minus sine squared is cosine squared. Cosine squared. And one of them cancels out the cosine in the numerator. And that's a proof. We want to establish this identity. Clearly, we start from the left-hand side. We're going to prove that it's 1. And on the left-hand side, we see tangent, cotangent, secant, cosecant. We're going to change everything to sine and cosine, which means this is going to be sine over cosine. This is going to be cosine over sine. This will be 1 over cosine. This will be 1 over sine. And this is a complex fraction. All we have to do is simplify, which means we multiply the top and the bottom by LCD, which is the product of sine and cosine. So let's multiply the top and the bottom by sine V cosine V. And let's see what happens. When you multiply this one by this one, cosine goes away, you get sine squared. And you multiply this one by this one, sine goes away, you get cosine squared. So this becomes sine squared plus cosine squared. When you multiply this one by this one, cosine goes away, and you get everything actually goes away. Simply they cancel each other. So let me quickly show you this. If you multiply by this one, gives you this. If you multiply by this one, gives you this. Multiplication of these two give us 1. Now we know sine squared plus cosine squared is 1, and we are done. 1 over 1 equals 1. We want to establish identities that involve arcs or angles that are negative. So obviously we start from the left-hand side. We know this means sine of negative theta to the second power. Let me just write one of them with detail so you see. This means going to write it up here. Or actually, okay, right here. Sine of negative theta to the second power. That's the meaning of it. So what is sine of negative theta? Is negative sine theta. What does this one mean? Cosine of negative theta to the second power. What is cosine of negative theta? Is cosine of theta. Okay. Sine of negative theta is minus sine theta, but cosine of negative theta is the same as cosine of theta. And because of that, we write it in this fashion. Sine of minus theta is minus sine theta. Cosine of minus theta is cosine theta. So when you square this, you get sine squared. When you square this, you get cosine squared. So you get sine squared theta minus cosine squared theta. This one is minus sine theta minus cosine theta. So again, I want to make sure we realize what's happening. This is minus sine theta minus cosine theta. All right, so for the numerator, we're going to factor it into sine theta minus cosine theta times sine theta plus cosine theta. And for the denominator, we just take the negative sign out. So the numerator is factored out. The denominator, we take a factor of -1 out. Sine theta plus cosine theta, they cancel each other. So we get sine theta minus cosine theta over -1. Let me write that. That means sine theta over -1, which is negative sine theta. That means minus cosine theta over -1, which means positive cosine theta. And that's cosine theta minus sine theta, and we just proved the identity.